Tonight, we're going to measure how long the universe can keep doing anything at all. Not how long it can keep expanding, not how long empty space can remain in existence, but how long the cosmos can preserve the differences that allow stars to shine, particles to interact, machines to run, chemistry to unfold, and life, wherever it may exist, to remain possible. The practical answer is almost impossible to absorb. Roughly 10 to the power of 100 years. A googol years. That is a 1 followed by 100 zeros. It is so far beyond the present age of the universe that our current 13.8 billion years would vanish inside it, like a single frame lost in a film longer than any civilization could ever watch. That number marks approximately when the largest surviving black holes may finally disappear through Hawking radiation, assuming the laws of physics continue behaving as our best theories predict. But there is a problem. The disappearance of the last black hole may not be the exact moment the universe reaches maximum entropy. It may only mark the last major step toward it. Perfect equilibrium could be something the universe approaches forever, without crossing one final, clearly marked line. By the end of tonight, you're going to understand why the last stars are only the beginning of the universe's long decline, why black holes control the final practical countdown, and why maximum entropy may have no single arrival time, even after almost every recognizable object has vanished. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Place a warm object beside a cold one. It could be a cup of coffee on a kitchen counter, a heated stone lying on winter ground, a piece of metal removed from a furnace and left in the air. At first, there is a difference. One object contains faster-moving particles, the surrounding environment contains slower-moving ones. Because that difference exists, heat can flow. The hot object cools. The cold surroundings warm. During that process, energy moves from one place to another. Something happens. Given the right machinery, part of that flow could even perform work. It could turn a tiny engine, generate an electrical current, or produce motion. The total amount of energy does not need to disappear for that opportunity to end. The opportunity ends when the temperature difference does. Eventually, the object and its surroundings approach the same temperature. Energy is still present in both. The particles have not vanished. The laws of physics have not switched off. But the useful difference is gone. That is the first mental model we need for the heat death of the universe. Maximum entropy does not mean that all energy has been destroyed. Energy is conserved in the physical processes we understand. Heat death means that the energy has become so evenly distributed, or so inaccessible, that no significant gradient remains from which organized work can be extracted. The universe runs not merely on energy, but on differences. Hot and cold, dense and diffuse, high pressure and low pressure, matter and antimatter, fuel and ash. A star shines because its core is hotter than its surface, and its surface is hotter than the space around it. A planet develops weather because one region receives more energy than another. A living cell survives because it continually moves matter and energy across boundaries. A machine turns because something pushes harder on one side than on the other. Remove every useful difference and the energy remains trapped in sameness. No engine can exploit it. No star can ignite from it. No sustained chemistry can build upon it. That is why the title's question is more subtle than it first appears. We are not searching for the moment when the universe contains nothing. We are searching for the point when whatever remains can no longer produce large-scale, organized change. And that journey will not end when the last familiar star goes dark. Stars are temporary reservoirs. They form from collapsing gas, burn through nuclear fuel, and release concentrated energy into colder space. Some will live for millions of years. Others, especially the smallest red dwarfs, may continue for trillions. But even the longest-lived stars eventually exhaust the conditions that keep them shining. When that happens, the universe will become darker, but it will not yet be still. White dwarfs will remain. Neutron stars will remain. Cold planets, failed stars, scattered particles, and black holes will remain. Gravity will continue pulling objects together, throwing them apart, and feeding some of them into larger remnants. Matter may still collide. Orbits may still decay. Black holes may still merge. Enormous stores of mass and motion will still exist. Darkness is not equilibrium. A room can be dark while furniture is falling, air is moving, and water is pouring across the floor. In the same way, the post-stellar universe can lose nearly all visible light while remaining thermodynamically unfinished. The final dominant objects are expected to be black holes. And black holes change the story because they are not simply cosmic containers where matter disappears. They carry entropy of their own, an extraordinary amount of it. In fact, the supermassive black holes at the centers of galaxies are believed to dominate the entropy associated with the material contents of the universe today. The bright stars filling the sky may look like the main event. Thermodynamically, they are not. A single supermassive black hole can contain vastly more entropy than all the stars surrounding it. As galaxies age, collide, and gradually lose their remaining organized structure, more of the accessible matter in a bound region may end up inside black holes. For a time so long that ordinary stellar history becomes almost irrelevant. Those black holes may be the last major concentrated structures left, but they are not eternal. According to Stephen Hawking's semi-classical calculation, black holes possess a temperature and emit extremely faint thermal radiation. A large black hole loses mass at an almost absurdly slow rate. The larger it is, the colder it is, and the longer it survives. A black hole with several times the mass of the Sun could endure for roughly 10 to the power of 67 years. A supermassive black hole survives far longer. And a future black hole assembled through mergers and feeding within a gravitationally bound region could push its lifetime toward the googol year scale, 10 to the power of 100 years. That is where the practical answer to our title comes from. Not from the death of the Sun, not from the last red dwarf, not even necessarily from the disappearance of ordinary matter. The countdown is set by the slow evaporation of the largest remaining black holes. Yet even here, the answer refuses to become simple. Suppose the final black hole disappears. Its mass has been converted into extremely dilute radiation. No stars remain. No planets remain in any active sense. No galaxy glows. No large, accessible reservoir of concentrated energy remains nearby. Has maximum entropy now been reached? Perhaps functionally, but perhaps not mathematically. The expansion of the universe introduces boundaries that do not appear in the warm object example. If cosmic acceleration continues forever, each observer will occupy a limited causal region surrounded by a cosmological horizon, a boundary beyond which events can never influence that observer again. That horizon has thermodynamic properties of its own. It possesses entropy. It possesses a temperature. And under the simplest model of permanent dark energy, the horizon may ultimately dominate the entropy accounting far more completely than every black hole, star, planet, and particle inside it. So the real question is already changing. We began by asking when the last useful engine shuts down. But before we can decide when the universe reaches maximum entropy, we have to understand what entropy actually measures, why physical systems move toward more probable arrangements, and why gravity makes the universe far stranger than a box of gas settling into stillness. Because the final state of the cosmos is not determined only by what remains inside space. It may also be determined by the boundary of the space any observer can ever reach. To understand that boundary, we first need a more precise picture of entropy itself. The word is often translated into something like disorder. That description is useful for a few seconds, then it starts causing trouble. A messy room may look disordered, but physics does not measure entropy by asking whether a human being thinks the room looks untidy. A neat stack of papers can have high entropy. A shattered glass can have lower entropy than another system that looks perfectly smooth. The important question is not whether a scene appears organized. It is how many microscopic arrangements can produce the same large-scale condition. Consider a box divided into two equal halves. On the left side, there are thousands of gas molecules. The right side is empty. A removable wall separates them. From a distance, the state is easy to describe. Gas on one side, vacuum on the other. Now remove the wall. The molecules begin moving across the full box. They bounce from its surfaces and collide with one another. After a short time, they are distributed throughout the available volume. Nothing is forcing each molecule to spread out according to a written command. Every molecule simply follows the laws of motion. Some move left, some move right, some reverse direction. At any instant, a few may even wander back toward the original half. But there are vastly more possible arrangements in which the molecules are spread across both sides than arrangements in which every molecule happens to occupy the left side together. That imbalance is almost impossible to exaggerate. The molecules could, in principle, all return to the original half through random motion. No basic law of mechanics assigns that arrangement a probability of exactly 0. But the number of possible spread-out arrangements is so overwhelmingly larger that a spontaneous return becomes effectively impossible for a macroscopic system. The gas moves toward the condition that can be realized in the greatest number of microscopic ways. That is the statistical heart of entropy. A macrostate is the large-scale condition we can describe: pressure, temperature, volume, density. A microstate is the exact hidden arrangement beneath it, the location and motion of every individual particle. Many different microstates can correspond to the same macrostate. When a system moves toward a macrostate compatible with more microscopic arrangements, its entropy increases. This way of thinking was developed through the work of Ludwig Boltzmann and others during the 19th century. Boltzmann helped connect the smooth quantities of thermodynamics, heat, pressure, temperature, to the motion and probability of enormous numbers of particles. That connection explains why the second law of thermodynamics feels so different from many other physical laws. Most microscopic laws do not obviously contain a preferred direction of time. If you watched a recording of two particles colliding, the reversed recording might still look physically possible. But watch cream mix into coffee. Watch smoke spread through a room. Watch an ice cube melt in warm water. Reverse those recordings and something looks immediately wrong. The reverse process may not violate the basic motion of any single particle. What makes it extraordinary is the required coordination. Trillions upon trillions of particles would need to move in precisely the right way at the same moment, selecting one exceptionally rare microscopic arrangement from an ocean of common ones. The second law is therefore not a mysterious force pushing objects toward ugliness. It is a statement about overwhelming statistical tendency. Systems move from less probable macrostates toward more probable ones. Concentrated conditions spread. Temperature differences shrink. Pressure differences equalize. Energy becomes shared among more degrees of freedom. And as that happens, the amount of energy available to perform organized work declines. Return to the warm object beside the cold environment. At first, the temperature difference provides an opportunity. A heat engine can place part of the flow between hot and cold reservoirs into controlled motion. But once both sides reach the same temperature, the molecules have not stopped moving. In fact, they may still contain a large amount of thermal energy. Their motion is simply no longer arranged as a useful imbalance. The system has reached equilibrium under those conditions. It has reached the state in which no spontaneous large-scale flow remains available. This is why maximum entropy does not need to resemble a frozen statue. At the microscopic level, particles may continue moving. Quantum fields may continue fluctuating, radiation may continue traveling. But without an accessible gradient, those motions cannot be assembled into a repeating engine that produces sustained macroscopic work. Energy remains. Direction disappears. This also explains why living organisms do not violate the second law. A cell is highly organized. It controls chemical reactions, repairs damaged structures, moves material across membranes, and stores information. A human body can maintain a temperature different from its surroundings. A forest can grow from air, water, minerals, and sunlight. If we looked only at the organism, it might appear that entropy is moving backward. But an organism is not a closed system. It absorbs concentrated energy and low entropy material. It releases heat and more dispersed waste into its environment. The local organization is maintained by increasing the entropy of the larger system. Earth does something similar on a planetary scale. Our world receives relatively concentrated energy from the hot surface of the sun. It eventually sends that energy back into space as more diffuse infrared radiation. The outgoing energy is spread across more wavelengths and more possible microscopic states. Between those two flows, weather can move, oceans can circulate, chemistry can build complex molecules, and life can exploit temporary differences. A refrigerator provides a smaller example. Inside the refrigerator, heat is removed from a cold compartment, left alone. Heat would flow inward from the warmer room. The refrigerator forces it in the opposite local direction. But the machine requires electrical power. Its motor and coils release even more heat into the room than was removed from the interior. Entropy decreases inside the compartment while increasing by a greater amount outside. Local orders allowed. The total accounting still moves forward. That distinction matters for the universe because nearly everything we value exists in a local departure from equilibrium. A star is hotter than surrounding space. A planet has one temperature at its surface and another deep inside. An atmosphere contains pressure differences. A chemical bond stores energy in a form that can later be released. A living system preserves boundaries between what is inside and what is outside. None of these arrangements is permanent. They are temporary patterns supported by larger flows. Heat death begins when the universe can no longer maintain enough of those differences to support new organized activity. But there is still a major weakness in the simple box of gas model. The box has fixed walls. Its particles do not significantly attract one another across the entire volume. The universe has neither of those convenient properties. Space expands. Gravity reaches across enormous distances. Matter can fall together instead of merely spreading apart. If we placed a cloud of gas in a large region and included its self-gravity, the smooth arrangement might not be the final equilibrium state. A slightly denser patch would pull more matter toward itself. The patch would grow. The gas would accelerate inward. Collisions would heat it. Radiation would escape. Eventually, the same system that began smooth and nearly uniform might produce a compact star surrounded by colder, emptier space. That looks like the opposite of the gas spreading through the box. Matter has become more concentrated. Structure has appeared. A glowing object has formed from something smoother. So has entropy fallen? No. But explaining why requires us to stop treating gravity as a minor correction. Gravity changes which states are available. It changes how energy is stored. It allows a system to become locally concentrated while releasing heat and radiation into a much larger environment. And when gravity is pushed to its most extreme limit, it produces objects whose entropy is greater than anything else we know how to place inside the same region. Black holes. Before we can follow the universe toward maximum entropy, we have to understand this first inversion. In a universe ruled by gravity, smoothness can be special. Clumping can increase entropy. And the brightest structures in the sky may not be the largest reservoirs in the thermodynamic story. The reason is that gravity does not behave like the walls of an ordinary box. In the simple gas example, particles spread because nothing strongly pulls the entire cloud back together. Once gravity becomes important, that assumption collapses. Take a large cloud of hydrogen. At first, imagine it spread almost smoothly through space. Every region contains nearly the same amount of matter. The cloud may look quiet, balanced, even simple. But perfect smoothness is fragile. One small region will always be slightly denser than another. It may contain a little more gas. It may be slightly cooler. It may move a little more slowly. That tiny difference is enough. The denser region exerts a stronger gravitational pull. More matter falls toward it. As more matter arrives, the region becomes heavier. Its pull grows stronger. The original imperfection amplifies itself. The cloud begins to collapse. At first, this seems to move entropy in the wrong direction. Matter that was spread through a large volume is becoming concentrated into a smaller one. A smooth distribution is turning into structure. But follow the energy. As gas falls inward, it accelerates. Gravitational potential energy becomes motion. Collisions convert that motion into heat. The collapsing cloud grows hotter. Radiation escapes into the colder space around it. The matter becomes more concentrated locally, but energy spreads outward through a much larger environment. A star forms in the center. Photons leave it. Heat enters space. The final state contains a compact object, a surrounding environment filled with radiation, and vastly more ways to distribute the energy than the original quiet cloud allowed. The clumping did not reverse the second law. Gravity created a new route for entropy to increase. This is one of the most important corrections in the entire story. Without gravity, a uniform gas often looks like equilibrium. With gravity, a perfectly smooth distribution can be a highly special condition, one capable of evolving into stars, galaxies, clusters, hot gas, radiation, and eventually black holes. The universe began remarkably smooth on large scales. Matter was not arranged into mature galaxies or enormous black holes. Tiny density variations were present, but the overall distribution was far more uniform than it is today. That smooth beginning contained extraordinary potential. Gravity had room to act. Small overdensities grew, gas flowed inward, dark matter gathered into halos, stars formed inside those halos, galaxies assembled, galaxies merged, matter fell towards central regions. The universe became more structured. At the same time, it produced more heat, more radiation, more particle motion, more collapsed objects, and more entropy. This is why the familiar image of entropy as everything becoming evenly spread is incomplete. For systems dominated by self-gravity, clumping and entropy growth can occur together. There is no single, universally accepted local formula that measures gravitational entropy in every possible space-time. Gravity is not simply another gas inside a container. The geometry of space-time itself responds to matter and energy. Horizons can appear. Information can become inaccessible. The system can no longer be described by ordinary pressure and temperature alone. But some parts of the picture are much clearer than others. We know that gravitational collapse releases energy. We know that stars radiate. We know that galaxies heat their gas through motion, collisions, and accretion. And we know that when enough mass is compressed inside a sufficiently small region, a black hole forms. That is where gravitational entropy becomes impossible to ignore. A black hole has an event horizon, a boundary beyond which signals cannot return to the outside universe. From the exterior, anything falling across that horizon becomes hidden. Its detailed microscopic information is no longer available to an observer who remains outside. This created a serious thermodynamic problem. Suppose you throw a hot object into a black hole. The object carries entropy. Before it crosses the horizon, that entropy is part of the visible physical accounting. After it crosses, the outside observer can no longer inspect the object or recover its microscopic state. If the black hole itself carried no entropy, then the measurable entropy outside would appear to decrease. That would threaten the second law. The solution was radical. The black hole must possess entropy of its own. And that entropy is connected not to the volume hidden inside, but to the area of the horizon. This is one of the strangest relationships in physics. For ordinary matter, we often expect capacity to scale with volume. A larger box holds more gas. A larger tank holds more water. Black hole entropy scales with surface area. As the mass of a non-rotating black hole increases, its horizon grows. The area grows roughly with the square of the mass. The entropy rises with that area. This scaling is enormous. A black hole does not need to look active to dominate the thermodynamic budget. It can appear dark, cold, and almost perfectly still. Yet its horizon represents an extraordinary number of possible underlying microscopic states. That changes how we should look at the present universe. Visually, stars seem to control everything. They produce the light. They illuminate the gas. They reveal the spiral arms of galaxies. They warm planets and make chemistry possible. But light is not a reliable map of entropy. The black holes at the centers of large galaxies may be almost invisible compared with the stars around them. Yet current estimates indicate that supermassive black holes dominate the entropy associated with the universe's material contents. Not the stars, not the planets, not the diffuse gas. The black holes. A single supermassive black hole can carry far more entropy than the stellar population of its host galaxy. Add the enormous population of galactic black holes across the observable universe, and the balance becomes overwhelming. The brightest structures are not the largest reservoirs. This inversion matters because the future universe will gradually transfer more of its remaining organized matter into precisely these objects. Stars burn fuel and leave remnants. Remnants interact. Gas falls inward. Galaxies merge. Central black holes grow. Some matter escapes into intergalactic darkness, but some crosses horizons and becomes part of the largest entropy reservoirs available inside gravitationally bound regions. The universe does not move from structure directly into featureless emptiness. It passes through an era in which entropy becomes concentrated in horizons. That phrase sounds contradictory. Entropy is often associated with spreading, yet black holes gather mass into compact regions. But the horizon is not simply a pile of compressed matter. It represents an extreme gravitational state with an immense number of possible microscopic configurations hidden behind one simple external appearance. From outside, a settled black hole can be described by only a few quantities: mass, rotation, and charge. Countless possible histories can produce the same outward result. A star may fall in. A planet may fall in. Hot gas, cold gas, light, dust, and other black holes may cross the horizon. The visible details disappear from the exterior description. The number of microscopic possibilities compatible with the same simple black hole becomes enormous. That is why black holes sit near the center of the entropy story. But they are still not the largest possible term in the final accounting. There is another boundary, much larger than any black hole horizon, that appears when cosmic expansion accelerates for long enough. It surrounds not an individual object, but the region of the universe that one observer can ever influence or receive information from. Its entropy may exceed the estimated entropy of today's material universe by an almost absurd margin. We're not ready to unpack that boundary yet. First, we need to follow the structures that gravity creates and understand what stars really do to entropy. Because stars are not machines holding cosmic decay at bay. They are among the most effective engines the universe has for turning concentrated gravitational and nuclear energy into diffuse radiation. They make planets warm. They make chemistry possible. They make complexity bloom. And while doing all of that, they drive the larger universe further in the direction it was already going. A star drives the universe forward by holding open a difference. Its center is compressed, hot, and dense. Its surface is cooler. The space beyond that surface is colder still. Between those regions, energy can move. Gravity first prepares the fuel, a cloud collapses, falling matter accelerates, collisions convert ordered infall into heat. When the central temperature becomes high enough, nuclear fusion begins. The star then enters a temporary balance. Gravity pulls inward. Pressure pushes outward. Fusion keeps replacing the energy that escapes from the surface. Nothing about that balance is permanent. It survives only while the star contains nuclei that can still release usable energy under the conditions in its core. Every photon leaving the surface carries part of that opportunity away. Near the star, the radiation is intense. It can strike a planet, warm an atmosphere, drive wind, circulate water, and push chemistry through reactions that would not proceed in a cold equilibrium environment. Farther out, the same light spreads across a larger sphere. Its energy becomes more dilute. The star creates local complexity by dispersing what gravity and nuclear binding had concentrated. That is why a shining star is not resisting the growth of entropy. It is one of the universe's most effective entropy engines. The star takes matter held in a special gravitational arrangement, converts nuclear fuel into radiation, and releases that radiation into colder surrounding space. The number of accessible microscopic arrangements grows. The energy becomes harder to gather back into its original form. Yet during the release, worlds can become active. On Earth, sunlight arrives from a surface thousands of degrees hotter than our planet. Earth absorbs a small fraction of that radiation and returns the energy to space at a much lower temperature. The total incoming and outgoing energy can remain close to balance. But the form changes. Hotter radiation arrives in a more concentrated stream. Cooler infrared radiation leaves in a more dispersed one. The difference between those flows supports almost everything active at the surface. Clouds form. Weather systems turn. Oceans move. Chemical bonds are built and broken. Living systems preserve fragile boundaries for a time. The complexity exists in the path between concentrated energy and dispersed energy. It does not cancel the larger thermodynamic direction. This gives stars a double role. They make organized activity possible, and they spend the conditions that make organized activity possible. Every second of light consumes some part of a finite reserve. For massive stars, the spending is violent. Their cores reach extreme temperatures. Fusion proceeds rapidly. They shine with enormous luminosity, but the brightness is purchased with a short life. Some survive only a few million years before their internal balance fails. A star like the Sun spends more carefully. It can remain stable for billions of years, converting hydrogen into helium while slowly changing the composition and temperature of its core. The smallest red dwarfs spend with extraordinary restraint. They are faint enough that many cannot be seen without a telescope, even when they are relatively nearby. Their interiors circulate material efficiently, allowing them to use a greater fraction of their hydrogen than a star like the Sun can reach. They do not preserve energy by breaking thermodynamics. They simply release it more slowly. That slow release makes them the final conventional stars. Long after massive stars have vanished, long after sun-like stars have left white dwarfs behind, red dwarfs will continue producing weak red light in a universe whose bright structures have already begun to fade. Their lifetimes may extend for trillions of years. The lowest mass hydrogen-burning stars may persist for many tens of trillions, perhaps toward the broad 100 trillion year scale depending on their mass and composition. By then, the present age of the universe will seem almost immediate. The cosmos is now about 13.8 billion years old. Against the life of the final red dwarfs, everything from the first galaxies to the present sky occupies only the opening portion of stellar history. But longevity is not permanence. A red dwarf still depends on a gradient. Its center must remain hotter than its exterior. Its material must still contain fusible nuclei. Its structure must still support the pressure required for reactions to continue. As hydrogen is converted, the internal conditions change. The star evolves. The reserve declines. The final stars may be patient, but patience does not create new fuel. At some point, the last naturally formed hydrogen-burning star reaches the end of its active life. There is no reason to expect this moment to be synchronized across all space. One bound region may lose its final star long before another. Distant regions may already have crossed beyond causal contact. But inside any one future gravitational island, the visible transformation will be unmistakable. The last red point weakens. Its spectrum changes. Its remaining fusion ends. The final ordinary stellar surface stops replacing the energy it radiates. For the first time since the earliest generations of stars, the accessible region contains no sustained natural furnace powered by conventional hydrogen fusion. That sounds like the end. It is not. The star leaves a remnant. The remnant may still be warmer than its surroundings. It still possesses mass. It still moves through a gravitational field. Other remnants continue orbiting elsewhere in the system. The last star removes one kind of free energy engine. It does not erase every difference. A white dwarf can cool. A neutron star can spin. Two compact objects can orbit. A planet can retain internal heat. A remnant can fall toward a black hole. A galaxy can continue redistributing orbital energy long after its light has vanished. The universe after stars is therefore not a motionless black screen. It is a dark mechanical system. Its active events become rarer. The intervals between them expand. Most of the time, almost nothing visible occurs. But the underlying matter is still arranged unevenly. Some objects remain tightly bound. Others occupy wide orbits. Some carry rotational energy. Some travel fast enough to escape if one encounter changes their direction. Gravity still has access to those differences. The disappearance of stars changes the dominant engine of the story. During the stellar era, nuclear burning makes cosmic change easy to see. After the stellar era, gravity works almost entirely without light. The future becomes quieter but not complete. A final red dwarf can fade, leaving no bright object anywhere in its accessible sky, while an enormous inventory of cold remnants continues moving through the dark. That is the false ending. The light is gone. The thermodynamic work is not. The final star has gone dark. For a while, its last radiation continues travelling outward. The photons cross the old planetary system, pass through the wider remnant population, and move into an increasingly empty region. Nothing replaces them. There is no neighbouring star waiting to rise. No cloud nearby is likely to collapse and begin another ordinary cycle. The sky becomes darker than any human night, but the system left behind still contains structure. Near the place where the star once shone, a compact remnant remains. Farther out, frozen planets follow altered orbits. Brown dwarfs drift through the region without ever having sustained conventional hydrogen fusion. White dwarfs and neutron stars circle the centre of the larger gravitational island. Smaller black holes may occupy invisible paths among them. The inventory is dark. It is not yet equilibrated. A white dwarf is a clear example. When a star like the Sun ends its active life, it leaves behind a dense core roughly comparable to Earth in size. The object no longer supports itself through ordinary fusion. Quantum pressure keeps it from collapsing further. At first, it is extremely hot. The white dwarf spends the future cooling. Energy escapes from its surface into colder space. The rate falls as the object loses heat. Its visible glow weakens until even that disappears. The process can continue across durations far beyond present cosmic history. The remnant is called dead because fusion has ended. Thermodynamically, it is still moving downhill. A neutron star can retain other differences. It may rotate rapidly. It may possess an intense magnetic field. It may orbit another compact object. Its original stellar engine is gone, but rotational, magnetic, orbital, and gravitational energy can still be released. A pair of compact remnants creates a particularly important reservoir. Two white dwarfs, neutron stars, or black holes may orbit their shared centre of mass. The motion is highly organised. The objects occupy a precise gravitational relationship. They disturb space-time as they move. Gravitational waves carry energy outward. The orbit shrinks. The bodies approach each other. If the process continues, they merge. The merger transforms one structured configuration into another while releasing energy into radiation, motion, heat, particles, or a newly formed black hole. That event may occur after an interval longer than the present age of the universe. Then the region becomes quiet again. Rare events define the post-stellar cosmos. A close encounter may send one cold planet inward. Two brown dwarfs may collide. Under unusual conditions, their combined mass could briefly support fusion. A white dwarf may pass close to another and exchange matter. A neutron star may merge with a companion. A remnant may wander near a black hole and disappear across its horizon. These events do not keep the universe continuously bright. They interrupt the darkness. The distinction matters because maximum entropy is not measured by how often a camera could record visible light. It is measured by whether the system still contains accessible arrangements capable of changing into more probable ones. A dark binary can still merge. A cold object can still fall. A nearly frozen white dwarf can still release heat into a colder environment. A galaxy with no stars can still rearrange itself gravitationally. The last starlight therefore answers only one question. It tells us when ordinary stellar fusion has become effectively absent. It does not tell us when organized work has become impossible. There is also no sharp universal date for the end of every stellar process. Low-mass stars evolve differently according to composition and exact mass. Rare collisions may produce temporary new stars after conventional star formation has ended. Some remnants can generate brief energetic events. The broad boundary near 10 to the power of 14 years is best understood as the end of the ordinary stellar era, not a stopwatch accurate to one final year. Beyond that boundary, the sources of usable energy become smaller, rarer, and more dependent on chance encounters. The universe enters what is often called the degenerate era. The name refers to the quantum state supporting compact remnants, not to moral decline or total inactivity. White dwarfs are supported by electron degeneracy pressure. Neutron stars rely on still more extreme forms of dense matter and nuclear interaction. Brown dwarfs, planets, and smaller bodies survive as cold material. Black holes wait among them. This era lasts so long that the stellar age becomes a brief opening act. The visible universe once displayed billions of galaxies filled with light. Now a future causal patch may contain only a gravitationally bound island of dark objects surrounded by accelerated expansion. Distant, unbound regions have moved beyond meaningful contact. The accessible inventory is finite. Every remaining event spends part of it. A collision reduces two objects to one. A merger converts orbital motion into radiation. A cooling remnant releases a finite store of heat. An ejected object removes mass and motion from future interaction with the bound system. A captured object increases the mass of a black hole while disappearing from the external inventory. The number of available pathways declines. The system does not become simple immediately. It becomes less connected. Connections are what make reservoirs useful. A planet and a star can exchange energy. Two remnants can exchange momentum. A body in orbit can fall inward. An isolated object beyond future contact may retain energy, but lose every practical path through which that energy could participate in a larger process. This is how the universe approaches heat death without needing to destroy everything. It reduces access. It widens separation. It converts active relationships into isolated survivors. The end of stars begins this transition visibly. The dark remnant era continues it mechanically. At first, a future galaxy may still contain vast numbers of compact bodies. They orbit through a shared gravitational field, passing one another across enormous distances. Direct impacts remain uncommon. Weak gravitational encounters do most of the work. One passage changes an orbit by a tiny amount. Another passage changes it again. Across enough time, those small exchanges accumulate. Some remnants gain energy. Others lose it. The dark galaxy begins sorting itself. A fraction of its objects move outward. A fraction move inward. The luminous identity of the galaxy is already gone. Now its gravitational identity slowly begins to dissolve. The next stage is not the death of one object. It is the evaporation of the system that once held the objects together. A dark galaxy dissolves through countless small decisions made by gravity. No intelligence chooses the outcome. No single encounter controls the system. Each remnant passes through the shared gravitational field and slightly alters the paths of others. Most changes are tiny. Over immense time, tiny changes become the architecture of the future. Consider two compact objects passing near one another. They do not collide. Their gravitational fields bend both trajectories. One leaves the encounter moving slightly faster. The other leaves slightly slower. Energy has been exchanged. Repeat this process across a population of white dwarfs, neutron stars, planets, brown dwarfs, black holes, and other remnants. The system begins to relax. Relaxation does not mean every object becomes still. It means the distribution of orbital energies evolves through repeated interactions. Some bodies move into wider paths, Others sink toward the center. A few acquire enough speed to escape the gravitational island entirely. This gradual loss of members is called dynamical evaporation. The word is descriptive, not literal. Nothing boils away from a surface. Individual objects are scattered outward until their velocities exceed the escape speed of the remaining system. Once an object escapes, it enters a very different future. It may continue moving forever through intergalactic space. Its internal structure can survive. Its mass and kinetic energy remain. But accelerated expansion and growing distance reduce the probability that it will ever meet another significant object. The remnant has not ceased to exist. It has become inaccessible to almost every useful relationship. The objects that lose energy move the other way. Their orbits tighten. They enter denser regions where encounters become more likely. A massive central object influences the sorting. Through a process known as dynamical friction, a heavy body moving through a background population can transfer momentum to surrounding objects and gradually sink toward the center. The name again can mislead. There is no ordinary surface rubbing against another. The resistance emerges from the gravitational wake created by the moving mass. A black hole passing through a field of remnants pulls some of them into a slightly denser trail behind it. The gravitational pull of that wake slows the black hole and transfers energy to the surrounding population. The heavy object moves inward. The lighter background gains energy. Some of those lighter objects later move outward or escape. Over time, the central region becomes a destination for the most massive survivors. Black holes meet other black holes. Compact objects form binaries. Three-body encounters become especially effective at reorganizing energy. A binary can pass near a third object. The encounter may tighten the binary while throwing the third object outward at high speed. The binary becomes more tightly bound. The ejected object carries away the released energy. The central system hardens itself by sacrificing members. This is one of the clearest ways gravity spends organized structure in the dark. The surviving binary stores more negative binding energy. The escaping remnant removes matter from the future interaction network. If the binary contains black holes, gravitational wave emission can eventually take over. The orbit contracts. The horizons merge. A larger black hole forms. The newly formed hole may remain near the center, or it may recoil. Gravitational waves can leave the merger asymmetrically, carrying more momentum in one direction. The final black hole receives a kick in the other. A modest kick shifts it away from the center. A stronger one can eject it from the gravitational island. This prevents the late universe from following one neat funnel in which every object inevitably enters one central hole. Some matter falls inward. Some is thrown outward. Some black holes merge. Some black holes escape. Some remnants occupy stable orbits for periods longer than entire earlier cosmic eras. The exact outcome depends on masses, trajectories, binary configurations, and the depth of the gravitational potential holding the region together. Yet the broad thermodynamic direction remains consistent. The network of possible interactions becomes thinner. Every ejection reduces the bound population. Every capture removes an external object. Every merger reduces the number of independently moving bodies. Every emitted gravitational wave carries organized orbital energy into a more dispersed form. A future galaxy may begin the degenerate era with billions of remnants. It does not preserve that richness indefinitely. The system gradually divides into a small central concentration and a growing population of isolated escapees. The process can take inconceivably long. As objects disappear, encounters become less frequent. The remaining system expands internally. Its members travel farther before meeting another significant gravitational influence. The rate of evolution slows because evolution has already removed many of the opportunities for further evolution. This creates a feedback towards silence. Early encounters prepare later isolation. The galactic structure does not need to collapse completely into one object. It can lose coherence by distributing its members beyond practical contact. Meanwhile, cosmic expansion separates the gravitational island from everything not already bound to it. The two processes operate at different scales. Internal gravitational relaxation empties the island. External accelerated expansion removes other islands from its future. An object ejected from the local system may find no larger cosmic environment waiting to receive it. Distant galaxies are no longer reachable. Their newly emitted signals may never arrive. The remnant enters a region where its only enduring relationships may be with the fields and horizon structure of its own causal patch. Accessibility has narrowed twice. First the object left the galaxy. Then the wider universe left causal contact. This is why the heat-death problem cannot be solved merely by counting how much matter survives. The same mass can have very different thermodynamic value depending on its relationships. A compact remnant in a tight binary can release orbital energy. The same remnant drifting alone beyond contact cannot. A planet near a warm star can support complex flows. The same planet in equilibrium with deep space cannot. A black hole surrounded by matter can grow. The same black hole in an empty patch can only wait for evaporation to dominate. The late universe is a process of breaking relationships. Not all at once. One orbit at a time. One ejection at a time. One merger at a time. Eventually, a gravitational island may contain only a few major survivors. Perhaps one very large black hole remains near the center. Perhaps smaller holes travel separately. Perhaps most ordinary remnants have been expelled. The details differ among causal patches. The narrowing is common. Yet before the external inventory disappears into black holes or isolation, one uncertainty remains inside the matter itself. The remnants are built from protons, neutrons, and electrons. If those particles are not permanent, the dark mechanical era has another route toward dissolution. If they are permanent, cold structure survives longer. Either way, gravity has already shown us the final pattern. Matter is being directed toward horizons or separated from every useful connection. Black holes may be waiting, but ordinary matter has not yet told us how long it intends to survive. A proton appears almost permanent by every human standard. Protons sit inside nearly every atomic nucleus. They help form rocks, oceans, planets, stars, living cells, and the dense remnants left after stars die. The protons inside your body have existed for billions of years. Many were already present before the sun formed. No experiment has ever confirmed the decay of a proton. That does not prove protons are eternal. It tells us only that if they decay through the channels scientists have tested, they do so extremely rarely. The distinction matters. A particle can remain unchanged through the entire history of the observable universe and still be temporary on a timescale of 10 to the power of 34 years. Cosmic time allows possibilities that laboratory time can barely touch. Within the standard model of particle physics, the proton is effectively stable. The known interactions do not provide an ordinary route for a lone proton to fall apart into light particles while conserving all the required quantities. But the standard model is not expected to be the final description of nature. It treats the electromagnetic, weak, and strong nuclear forces with extraordinary success. Yet it does not include gravity in the same quantum framework. It does not explain every observed particle property. It does not tell us why the strengths of the forces take the values they do. Many proposed grand unified theories attempt to connect the strong force with the electroweak interaction at extremely high energies. In some of those theories, the separation between quarks and leptons is not absolute. Processes that are impossible at ordinary energies become possible through extraordinarily rare quantum transitions. A proton could decay. One possible channel would turn it into a positron and a neutral pion. The pion would then decay into photons. Other theories predict different final particles. The exact channel matters because an experiment must know what pattern to search for. This is where the question leaves the deep future for a moment and enters a real chamber beneath a mountain in Japan. Super Kamiokande is an enormous underground detector filled with highly purified water. Thousands of light-sensitive instruments line its inner walls. The mountain above shields the detector from much of the constant rain of particles striking Earth from space. Inside the water are staggering numbers of protons. Most abound inside the nuclei of hydrogen and oxygen atoms. The experiment waits for one of them to produce the unmistakable pattern expected from a decay. If a proton transformed into a positron and a neutral pion, the outgoing particles would move through the water and create faint cones of Cherenkov light. Sensitive detectors could record the rings. The event would last only an instant. Its meaning would reach into the far future of every ordinary object. So far, the expected signal has not appeared at a statistically convincing level. That absence allows physicists to calculate a lower limit on the proton's partial lifetime for particular decay modes. For some of the most carefully tested channels, those limits exceed 10 to the power of 34 years. This number is easy to misunderstand. It does not mean scientists have measured a proton and found that it will decay after exactly that long. It does not mean the average proton is expected to survive until a scheduled date. It means the experiment has watched enough protons for enough time that more frequent decay would probably have produced detectable events. The lower limit moves outward. The actual lifetime could be much longer, or the proton may never decay through those channels at all. That leaves the future universe divided into two broad paths. On the first path, proton decay is real. After the stellar era, cold matter continues existing for an immense period. White dwarfs, planets, asteroids, and isolated fragments drift through darkness. Then, very slowly, their protons begin to disappear. Not all at once. There is no universal flash. One proton decays inside one object. Much later, another decays somewhere else. Each event releases lighter particles and radiation. Across a timescale beyond ordinary comprehension, the material loses mass. A cold planet does not explode like a bomb. Its structure gradually becomes impossible to maintain as more of the particles supporting it vanish or transform. White dwarfs slowly erode. Atomic nuclei disappear. Objects that once seemed solid become increasingly diffuse collections of lighter particles. The matter is not destroyed into nothing. Energy, momentum, and the relevant conserved quantities continue through the decay products. But the organized baryonic structures dissolve. Another category of long-lived cosmic architecture is removed. On the second path, the proton is stable. Planets, white dwarfs, neutron-rich remnants, and isolated pieces of matter can persist much longer. Their temperatures may fall toward the temperature of the surrounding environment. Their internal energy may become almost impossible to use, but their particles remain. Even here, survival does not mean activity. A cold rock drifting beyond meaningful contact with every star may endure while contributing almost nothing to organized cosmic work. A white dwarf could remain compact and dark after its accessible thermal gradient has nearly disappeared. Matter can persist after usefulness is gone. That is the same distinction we met at the beginning. Existence is not free energy. A universe filled with stable, isolated particles can still approach heat death if those particles cannot be assembled into sustained processes that exploit meaningful differences. Stable matter also remains subject to gravity. A remnant may collide with another. It may fall into a black hole. It may be ejected into isolation. It may undergo extremely slow quantum or gravitational processes that become relevant only because the available time is so vast. The no-decay branch therefore contains more surviving material structure, but it does not restore the bright stellar universe. It only changes the inventory carried into the deepest future. There are more exotic possibilities. Some theories suggest that black dwarfs, white dwarfs cooled over unimaginable periods, could undergo rare transformations. Dense remnants may experience reactions that are negligible today. Neutron stars may evolve through processes we cannot test across those timescales. These ideas depend heavily on uncertain particle physics. They cannot be treated as scheduled stages. What matters for our main question is simpler. Proton decay changes the route toward heat death more than it changes the destination. If protons decay, ordinary matter gradually converts into lighter particles and radiation. If protons remain stable, cold matter survives as increasingly isolated structure. In both cases, usable gradients continue declining. In both cases, Accelerated expansion separates distant regions. In both cases, gravitational interactions push some accessible matter inward and throw some outward. And in both cases, black holes remain capable of surviving far longer than stars or planets, or ordinary remnant activity. The two paths converge at the horizon. A proton that decays outside a black hole adds particles and radiation to the surrounding universe. A proton that falls across an event horizon becomes part of the black hole's mass. A stable planet may orbit for a very long time, but one gravitational encounter can redirect it toward capture or eject it beyond future contact. A decaying white dwarf may disperse before a black hole reaches it. A stable white dwarf may eventually be swallowed. The details differ. The larger entropy story continues. This is why proton decay must remain a branch, not a foundation. We cannot build the entire future timeline on an event no one has observed. We can state what experiments have excluded. We can state what theories permit. We can follow both outcomes far enough to see where they agree. They agree that the era of ordinary matter is not the final thermodynamic era. Something survives longer. Something stores more entropy. Something becomes colder as it grows larger and lives longer as it gains mass. Black holes remain after the stellar engines stop, and after the fate of protons has divided the future into competing possibilities. But following the last objects has carried us only halfway toward the answer. We have counted stars, remnants, particles, and black holes as though the universe were merely a collection of things. Maximum entropy demands a larger accounting. The final system includes not only the objects that remain within reach, but the boundary separating what can still affect an observer from what has been carried permanently beyond contact. Before we can decide whether the last black hole marks the end of the countdown, we must change the question. Not only what survives, but what entire region are we measuring? The region we are measuring is not the entire universe in any simple sense. That phrase, the entire universe, sounds precise until cosmology forces us to ask what it includes. Does it mean everything that exists? Everything whose light has reached us? Everything that can ever affect us? Everything inside one future horizon? Those are not the same region. Until now, we have followed the contents of the universe. Stars, remnants, particles, galaxies, black holes. We have asked which objects survive and which processes continue after the light fades. That was the first task. Now the task changes. To understand maximum entropy, we must determine the full thermodynamic system being counted. And in an accelerating universe, that system is shaped by a boundary no spacecraft can touch and no observer can see as a solid surface. A cosmological horizon. The word horizon is familiar. On Earth, the horizon marks the limit of what you can see from one location. Walk forward, and the boundary moves with you. Nothing physically special exists on the ground beneath that distant line. A black hole horizon is more serious. It separates events that can still send signals outward from events that cannot. A cosmological horizon is different again. It emerges because space itself expands. Imagine two distant galaxies. Light leaves one and begins traveling toward the other. Locally, the light always moves at the speed of a light. Nothing overtakes it through nearby space. But while the light travels, the space between the galaxies expands. If the expansion behaves in the right way, especially if it continues accelerating, the separation can grow so rapidly that light emitted after a certain time will never complete the journey. The light does not turn around. It does not hit a wall. It keeps moving locally forward. The destination simply recedes through expanding space in such a way that the signal never arrives. That creates a future event horizon. Events beyond that boundary may exist. Their local physics may continue normally. Stars may burn there. Black holes may merge. Particles may collide. But no new signal from those events can ever reach the observer at the center of the causal region. They are no longer part of that observer's accessible future. This is not identical to the edge of the observable universe. The observable universe is defined largely by the light that has had time to reach us since the early cosmos. It is a record of what we can presently see. A future event horizon answers a different question. What can ever influence us from now onward? Some objects we can observe today are already so distant that signals they emit in the far future will never reach us. We see their ancient light, but we will not remain in causal contact with their entire future. The visible map and the accessible future are different maps. For entropy, that distinction matters. Thermodynamics asks what states are available to a system and what information can move between its parts. If a region becomes permanently inaccessible, it cannot function as a future reservoir from which an observer extracts energy or receives new information. This does not mean the inaccessible region has ceased to exist. It means it has left the causal accounting for that observer. So instead of trying to assign one simple finite entropy to an entire universe that may be spatially infinite, we focus on one causal patch, the finite region whose contents can still influence a particular observer. That gives the title a more defensible frame. We're asking how long it takes one accessible cosmic region to lose its usable differences and approach its highest available entropy state. Now the strange part begins. The boundary of that region is not thermodynamically empty. In the 1970s, Gary Gibbons and Stephen Hawking extended the connection between horizons and thermodynamics beyond black holes. In a universe dominated by a positive cosmological constant, the simplest mathematical model for permanent dark energy, a cosmological horizon has a temperature. It also has entropy. This result is easy to state and difficult to absorb. Empty expanding space can possess a horizon with thermodynamic properties. The horizon is not made of ordinary material. It is not a shell of particles surrounding the observer. It arises from the causal structure of space-time. Yet the information hidden beyond it contributes to the thermodynamic description in a way deeply related to the area of the horizon. The same broad lesson that appeared around black holes returns on a larger scale. Horizons count, and the cosmological horizon may dominate the final entropy budget more completely than every object inside it. Recall the inversion we encountered earlier. The stars dominate the visible universe, but supermassive black holes dominate the estimated entropy associated with its present material contents. Under common cosmological estimates, the combined entropy associated with those black holes lies around 10 to the power of 104 times Boltzmann's constant, though the exact total depends on uncertain black hole populations and masses. The entropy associated with a de Sitter-like cosmological horizon can lie near 10 to the power of 122 times Boltzmann's constant under the simplest permanent cosmological constant model. The gap is enormous. It is around 18 orders of magnitude. A billion is 9 orders of magnitude. The difference is like multiplying by a billion, and then by another billion. The objects we have followed may occupy only a tiny fraction of the total entropy capacity of the final causal region. This changes the architecture of the story. We cannot simply say, the stars die, the matter decays, the black holes evaporate. Maximum entropy is reached. The disappearance of the objects is only one side of the accounting. The horizon changes too. Consider a black hole inside a universe with a positive cosmological constant. The black hole has its own horizon. Farther away, the observer has a cosmological horizon. The presence of mass affects the geometry between them. The system contains more than one thermodynamic boundary. As the black hole changes, the horizon structure of the entire causal patch changes. When matter falls into the black hole horizon grows. When the black hole loses mass, its horizon shrinks. As mass leaves the localized black hole and the system moves toward an emptier, de Sitter-like state, the cosmological horizon can approach a larger equilibrium area. The black hole may lose entropy as it evaporates. The radiation carries entropy. The cosmological horizon's contribution changes. The total generalized entropy can still rise. This is why maximum entropy cannot be located by watching only the final object disappear. The correct quantity is not the entropy of the black hole alone. It is the combined entropy of matter, radiation, black hole horizons, and the cosmological horizon relevant to the causal patch. The boundary is part of the system. That does not make every detail settled. The microscopic meaning of cosmological horizon entropy remains connected to deep unresolved questions in quantum gravity. Physicists do not yet possess a complete theory explaining all the fundamental states counted by the horizon area. Dark energy itself may not be a permanent cosmological constant. If it changes over time, the horizon can change with it. The maximum entropy available to the causal patch may change. The final equilibrium state may not be the empty de Sitter condition described by the simplest model. Those uncertainties will matter later. For now, the primary route remains clear. If accelerated expansion continues in approximately its current form, distant unbound regions leave causal contact. Each surviving observer is left inside a limited patch. Inside that patch, stars die. Remnants interact. Matter may decay or persist. Black holes grow, merge, and eventually evaporate. Throughout that evolution, the cosmological horizon forms the outer thermodynamic boundary. This midpoint changes the question completely. We are no longer asking only which object lives the longest. We are asking how the disappearance of those objects alters the entropy of the entire accessible region. We are no longer following a museum of cosmic remains. We are tracking information across horizons. The final black hole still matters. Its lifetime still sets the practical timescale near 10 to the power of 100 years. But its evaporation must now be understood as one transition inside a larger horizon-bound system. And to understand that transition, we need to look more closely at the black hole itself. Why does its entropy depend on area? Why does greater mass make it colder? And how can an object lose entropy while the universe around it moves closer to its maximum? The thermodynamics of a black hole began as an attempt to prevent the second law from failing. In the early 1970s, Jacob Bekenstein considered what happens when entropy is dropped into a black hole. Take an ordinary physical system. It may contain heat, chemical structure, radiation, or information encoded in the arrangement of matter. As long as the system remains outside the horizon, its entropy belongs to the accessible universe. Then it falls. After crossing the event horizon, no signal carrying its detailed state can return to the exterior. To an outside observer, the accessible entropy appears to have decreased. If a black hole contributed nothing to the accounting, the second law could be defeated simply by throwing entropy across a horizon. Bekenstein proposed that the horizon itself must carry entropy. The suggestion was not a decorative analogy. The black hole needed a genuine thermodynamic quantity capable of increasing when matter entered. General relativity had already supplied a clue. Under ordinary classical processes, the area of a black hole horizon does not decrease. Feed the hole, and the area grows. Merge black holes, and the final horizon obeys an area relation resembling the second law's treatment of entropy. Bekenstein connected the two. Black hole entropy should be proportional to horizon area. The proposal was strange because a classical black hole was not thought to have a temperature. It absorbed radiation but emitted none. Thermodynamic entropy without temperature looked incomplete. Stephen Hawking approached the problem through quantum fields and curved space-time. The calculation changed the status of black holes permanently. A black hole is not perfectly black. To a distant observer, it produces thermal radiation. That radiation gives the black hole a temperature. The temperature is inversely related to mass. A larger black hole is colder. A smaller black hole is hotter. The two discoveries lock together. Bekenstein's horizon entropy and Hawking's temperature produced a consistent thermodynamic object. The proportionality constant could now be fixed. The entropy of a black hole is determined by the area of its horizon in units set by fundamental constants, including gravity, quantum mechanics, and the speed of light. This relationship is one of the deepest bridges in modern physics. It ties geometry to information. A two-dimensional area appears to measure the number of microscopic possibilities associated with a three-dimensional gravitating system. The full microscopic interpretation remains unfinished. Quantum gravity approaches do not all describe the underlying states in the same way, but the thermodynamic result is not optional. Black holes behave as systems with entropy and temperature. That behavior repairs the original second law problem. When matter falls inward, ordinary entropy outside may disappear from direct access, but black hole entropy increases. The relevant rule becomes broader than the ordinary second law. It is called the generalized second law. Add the entropy of matter and radiation outside the horizons to the entropy assigned to the horizons themselves. The total should not decrease. This is the ledger required for the far future. A black hole can gain entropy while swallowing matter. It can later lose its own horizon entropy while evaporating. The emitted radiation carries entropy outward. Other horizons in the space-time also participate in the full accounting. No one component needs to increase at every moment. The generalized total is the quantity that continues toward its maximum. The area scaling makes black holes extreme. For a simple, non-rotating black hole, the horizon radius grows in direct proportion to mass. Area grows with the square of that radius. The entropy therefore grows roughly with the square of the mass. Combine matter into one larger black hole, and the entropy can become far greater than the entropy carried by the same material in ordinary stellar form. This is why black holes matter so much to the final timeline. They are not merely long-lived remnants. They are enormous thermodynamic reservoirs, yet their temperature scaling points toward their destruction. A massive black hole is extraordinarily cold. At the present epoch, the cosmic microwave background is warmer than the Hawking temperature of any large astrophysical black hole. Starlight, gas, dust, and other radiation also enter the horizon. The hole gains more energy than it loses. Net evaporation is delayed. The universe must cool around it first. Expansion stretches the background radiation. The wavelengths grow. The temperature falls. Stars stop contributing new light. Matter is captured, expelled, or diluted. Eventually, the environment drops below the black hole's temperature. The balance reverses. More energy leaves through Hawking radiation than enters from outside. The black hole begins a net loss of mass. At first, almost nothing seems to happen. The temperature is so low that the emitted power is minute. The horizon shrinks by a negligible amount across times that exceed the lives of stars. But the loss changes the temperature. Less mass means a hotter hole. A hotter hole radiates more strongly. Stronger radiation removes mass faster. The process accelerates. The final phase is much shorter and more energetic than the long quiet lifetime that precedes it. This creates the last apparent conflict with entropy. As the horizon shrinks, black hole entropy falls. But the radiation outside becomes more entropic. The energy is no longer stored in one compact gravitational object. It is spread across many possible field states over an expanding region. Inside a universe with a cosmological horizon, the outer boundary must be included as well. The disappearance of localized mass changes the geometry of the causal patch. As the patch approaches an emptier de Sitter-like state, the cosmological horizon approaches its own equilibrium area. The black hole's entropy decreases. Radiation entropy appears outside. The cosmological contribution adjusts. The generalized total continues upward. This is the mechanism that allows the final black hole to evaporate without reversing the thermodynamic direction of the universe. The black hole is not the maximum by itself. It is a temporary concentration inside a system with a larger possible horizon entropy. Its existence keeps the patch away from final equilibrium. Its evaporation carries the patch closer. What remains is to measure the duration. The black hole has entropy proportional to area. It has temperature inversely proportional to mass. It loses energy through radiation. Combine those relationships, and a remarkable clock appears. The lifetime grows not directly with mass, and not with the square of mass, but approximately with the cube. The clock grows with the cube of the black hole's mass. That single relationship is the reason black holes can outlive stars by such an extreme margin. If one black hole contains twice the mass of another, its evaporation lifetime is not merely twice as long. Under the simplest Hawking calculation, it is roughly 8 times as long. Double the mass, cube the difference. 8 times the lifetime. Increase the mass by a factor of 10, and the lifetime rises by roughly a factor of 1,000. That is the scaling hidden behind the enormous numbers waiting in the far future. The reason begins with temperature. A larger black hole has a larger horizon, but it has a lower Hawking temperature. Its radiation is weaker. It loses mass more slowly. A smaller black hole is hotter. It radiates more strongly. It loses mass faster. So a large black hole receives 2 forms of protection from rapid evaporation. It contains more mass to lose, and it loses that mass at a lower rate. The combination produces the cubic lifetime law. This is not a minor adjustment. It transforms mass into time at a terrifying rate. Start with a black hole roughly comparable to the Sun in mass, depending on the exact assumptions and constants used. Its evaporation lifetime is of order 10 to the power of 67 years. That is already beyond almost every other astrophysical timescale. The longest conventional stars may live for trillions of years. A solar mass black hole survives for a number of years, written with roughly 67 powers of 10. The stellar era disappears inside that interval. The entire present age of the universe disappears inside it. Even the hypothetical era of proton decay, if protons are unstable on scales near 10 to the power of 34 years, would finish unimaginably earlier. Now increase the black hole's mass. A black hole containing 1 million solar masses is not unusual by galactic standards. Objects in this broad range occupy the centers of many galaxies. 1 million is 10 to the power of 6. Cube that mass increase, and the lifetime grows by approximately 10 to the power of 18 relative to the solar mass case. The result moves toward a lifetime of roughly 10 to the power of 85 years. The exact number shifts with spin, charge, particle species, and the assumptions built into the calculation. The order of magnitude is what matters. The black hole does not merely survive longer than a star. It survives so long that the entire history of stars becomes a negligible prelude. Now consider a black hole with 1 billion solar masses. That is 10 to the power of 9 times the mass of the Sun. Cubed, that mass factor becomes 10 to the power of 27. Add it to the solar mass lifetime scale, and the evaporation time moves toward roughly 10 to the power of 94 years. 1 billion solar mass black hole spends almost all of that existence emitting an incredibly weak thermal glow. It does not roar through the ages. It barely changes. For intervals that make galaxies seem temporary, its horizon shrinks by amounts too small to matter on any familiar scale. The black hole is not inactive. Quantum fields continue producing radiation. Energy continues leaving. But the process is so slow that the object appears almost permanent. This is why the final black hole era is dominated by patience rather than violence. The popular image of evaporation often focuses on the end. A shrinking black hole becomes hotter. Its radiation intensifies. The mass loss rate accelerates. The final stages may be energetic, but that dramatic phase is not representative of the black hole's life. Imagine a candle that burns almost imperceptibly for nearly its entire existence, then consumes its final fragment of wax rapidly. The flash at the end may attract attention. The waiting defines the lifetime. For a supermassive black hole, almost all the waiting occurs at temperatures far below anything in the present universe that we would call warm. Today, these black holes do not evaporate cleanly because their surroundings still feed them. The cosmic microwave background is warmer than the Hawking temperature of a large astrophysical black hole. Starlight, gas, dust, and other matter can also fall inward. Even a small amount of absorption can exceed the black hole's feeble radiation loss. But the environment cools. Cosmic expansion stretches background photons to longer wavelengths. Stars disappear, gas becomes sparse, matter is captured, ejected, decayed, or carried beyond contact. Eventually, the incoming energy becomes weaker than the outgoing Hawking radiation. Only then does the black hole begin its long net decline. The mass-cubed law tells us how long that decline can last once evaporation dominates. But it does not yet tell us the mass of the final black hole. That depends on the history of its region. Black holes can merge. They can absorb stars and remnants. They can consume gas. A central black hole may grow through repeated galactic mergers while the universe is still young enough for galaxies to meet. Later, compact remnants can continue falling inward. Several black holes within one bound region may combine into a larger one. Each merger pushes the lifetime outward. Suppose two similar black holes merge and retain most of their combined mass after gravitational wave losses. The new object is nearly twice as massive as either original whole. Its expected evaporation lifetime is therefore not merely the sum of their separate lifetimes. Because lifetime rises approximately with mass cubed, the combined whole can survive several times longer than either one would have survived alone. Concentration extends the clock. This is the route toward the googol year estimate. A black hole already containing billions of solar masses can survive near the 10 to the 94 year range. If future mergers and captures create still larger holes, perhaps containing tens of billions, hundreds of billions, or more solar masses inside a bound region, the lifetime can be pushed farther outward. Eventually, plausible extreme scenarios approach 10 to the power of 100 years. A googol years. That number should not be treated as a precise appointment. There will be no universal alarm set for exactly 1 googol years from now. The lifetime depends on mass. It depends on whether the black hole rotates. It depends on which particles can be emitted. It depends on whether unknown physics changes the final stages. It depends on how much matter remains available to feed the hole before its isolation becomes complete. Most importantly, it depends on what the phrase "the last black hole" means. The universe may be spatially enormous or infinite. Distant regions become causally disconnected under continued accelerated expansion. Their black holes do not gather into one final object. Different causal patches can contain different final masses. One region may end with a black hole assembled through many mergers. Another may contain smaller isolated holes. A third may lose most of its remnants through gravitational ejection. The practical answer to the title therefore concerns the longest-lived black holes inside an accessible region, not one universal object ruling all of existence. Still, the order of magnitude remains powerful. 10 to the power of 100 years is not chosen because it sounds dramatic. It emerges from combining 3 physical facts. Black holes radiate. Larger black holes are colder. Their lifetimes rise approximately with the cube of their mass. Those facts carry us from stellar mass holes surviving around 10 to the power of 67 years, through galactic black holes surviving toward 10 to the power of 94, and into extreme future masses capable of approaching the googol year scale. By then, every familiar astronomical age is over. Stars have vanished. Galaxies have lost their luminous structure. Ordinary matter may have decayed or become isolated. The cosmic microwave background has been stretched to extraordinary wavelengths. The surviving black hole is colder than almost anything that came before it. For nearly all its remaining life, it emits only a faint trickle of energy into an almost empty causal region. Then the rate begins to rise. The horizon shrinks. The temperature increases. The last fraction of mass disappears much faster than the first. And at the end, the black hole that carried the practical countdown is gone. That is the event behind our numerical answer. But the calculation still contains one unresolved variable. We know how lifetime depends on mass. We do not yet know what mass the final black hole in a real future causal patch will possess. That mass will be determined by everything gravity does before the region becomes completely isolated. Every merger, every capture, every ejection, and every object that either reaches the horizon or escapes it forever. Imagine one gravitational island in the far future. It may descend from a local group of galaxies that remained bound while more distant structures disappeared beyond causal contact. The bright galaxies are gone in their original form. Their stars have died. Their gas has been consumed, heated, expelled, or captured. What remains is a loose population of compact objects moving through a shared gravitational field. Near the center is a supermassive black hole. It did not begin as the final object. It became the final object through history. Early galactic mergers brought central black holes into the same bound system. Some formed binaries. Gravitational interactions and surrounding matter reduced their separation. Gravitational waves completed the final approach. Each successful merger increased the mass of the central hole. Part of the system's energy escaped as gravitational radiation, but most of the combined mass remained behind the new horizon. The result was colder than either predecessor and capable of surviving far longer. Later, ordinary feeding declined. The remaining gas became sparse. Stars disappeared. The central hole entered a slower phase of growth controlled by compact remnants and smaller black holes. A white dwarf passed near the dense center and had its orbit altered. It did not fall in immediately. It returned again and again across enormous intervals. Each passage through the crowded central region exposed it to further gravitational encounters. Eventually, one interaction removed enough orbital energy to send it inward. The white dwarf crossed the horizon. The central black hole gained mass. Much later, a binary containing two smaller black holes entered the same region. A three-body encounter hardened the binary and ejected another remnant. Gravitational radiation then drew the pair together. Their merger produced a larger hole. The newly formed object received a recoil kick. This time, the kick was not strong enough to escape the island. The hole moved away from the center, slowed through gravitational interactions with the remaining population, and gradually returned. Another branch of the same history could have ended differently. A stronger kick might have removed the merger remnant permanently. The future mass of the central black hole depends on these contingencies. Capture builds it. Recoil can remove its competitors or remove the central object itself. Ejection empties the surrounding population. Accelerated expansion prevents help from arriving outside the bound island. There is no universal final mass written into the laws of physics. There is only the mass assembled by one region before its opportunities close. As the island ages, encounters become rarer. Objects at large distances are slowly scattered away. Some exceed the escape speed and depart. Others lose energy and move inward. The population thins from both directions. The black hole gains a fraction of the original material. The rest becomes isolated. This limits its growth. The hole cannot consume matter that has already been ejected beyond future contact. It cannot merge with black holes in distant gravitational islands. Cosmic expansion has placed those regions beyond causal reach. Even if infinitely many black holes exist elsewhere in a larger cosmological model, they do not contribute to this object's future. The final black hole is local to the causal patch. Its mass is local. Its evaporation time is local. Within this one island, the last significant capture may occur after an interval longer than the entire stellar era. A cold remnant approaches. The encounter produces a weak burst of radiation or particles. The object crosses the horizon. Then no comparable object remains on an orbit capable of reaching the center. The island has reached the end of meaningful feeding. A few smaller bodies may still exist far away. Some are already escaping. Others occupy paths so stable and distant that interaction times exceed the remaining black hole lifetime. They contribute almost nothing to the central future. The black hole is now effectively alone. Its mass has reached the value that matters for the final clock. If the assembled whole contains billions of solar masses, its Hawking lifetime lies toward the 10 to the power of 94-year scale. If the history of the island produced a still more massive object through repeated mergers and capture, the lifetime can move farther outward. For extreme future masses, the estimate can approach 10 to the power of 100 years. The number does not come from assuming that every particle in the universe enters one hole. It comes from extending the mass-cubed lifetime law to the largest holes that one bound region could plausibly assemble. The distinction removes false precision. Another causal patch can produce a different final hole. One region may lose its central black hole through recoil. Another may retain several isolated holes instead of one dominant survivor. Another may contain a deeper gravitational potential and assemble a larger final mass. Their practical heat-death times need not match exactly. No observer could gather the results into one universal comparison after the regions become causally disconnected. Inside our chosen island, the environment continues cooling. The cosmic microwave background has been stretched to extremely long wavelengths. No ordinary star contributes meaningful radiation. The remaining particles are sparse. For a long period, the background may still be warmer than the hole's Hawking temperature. The black hole absorbs slightly more than it emits. Expansion continues, reducing their incoming bath. Eventually, the two temperatures cross. The surrounding universe becomes colder than the black hole. Net evaporation begins. The assembly history is finished. The mass-cubed clock is now running only downward. The black hole emits at an almost negligible rate. Its horizon loses an imperceptible amount of area. No galaxy remains around it in the familiar sense. No reservoir is available to reverse the decline. The history that created the hole is narrowed into one final thermodynamic process. A localized horizon inside a cosmological horizon. A finite mass. A temperature slightly above its environment. A lifetime determined by the mass the island managed to preserve. This is the physical meaning of the last black hole, not the ruler of the entire universe. The final major engine inside one accessible future. Before we follow its evaporation to the end, the assumptions beneath that future must survive one last test. Dark energy must preserve the horizon structure. The vacuum must remain stable. Quantum gravity must not replace evaporation with a radically different final state. The island has built the clock. Now we must ask whether the universe allows it to finish. The clock can be broken in several ways. But not every uncertainty deserves equal weight. Some possibilities would change only the details of the far future. Others would erase the entire black hole timeline before it has time to unfold. The strongest challenge begins with dark energy. Our standard path assumes that the accelerated expansion of the universe continues indefinitely, and he eventually resembles a state dominated by a positive cosmological constant. Under that assumption, distant unbound structures disappear beyond causal contact. Each surviving gravitational island becomes increasingly isolated. A cosmological horizon surrounds the accessible patch. Black holes eventually evaporate inside that horizon, and the system moves toward an empty de Sitter-like equilibrium. But observations do not reveal the ultimate nature of dark energy directly. They reveal how the expansion has behaved across the part of cosmic history we can measure. A cosmological constant is the simplest explanation. Its density remains fixed as space expands. Matter and radiation dilute, but the vacuum contribution does not. Over time, it dominates more completely. If that model is correct, the broad architecture we have followed remains intact. The causal horizon persists. The background approaches a very low but non-zero horizon temperature. Black holes disappear. The accessible region moves toward its maximum generalized entropy. But dark energy may not be perfectly constant. It could arise from a field that evolves slowly over time. Its density or pressure could change. The acceleration might weaken, strengthen, or eventually reverse. Each possibility changes the horizon. If the acceleration weakens enough, the future event horizon may differ from the one predicted by a permanent cosmological constant. Regions that would otherwise become inaccessible might remain connected for longer. The maximum entropy assigned to one causal patch could change because the size and nature of the patch itself would change. If dark energy strengthens dramatically, expansion could become increasingly violent. Galaxies might separate more rapidly. Bound systems could eventually be disrupted under extreme models. The universe might not wait calmly for black holes to evaporate over googol years. The structure of space-time could destroy the conditions supporting those objects earlier. If the acceleration eventually ends and cosmic expansion reverses, the final state could be completely different. Distant matter might return to causal contact. Temperatures could rise. Gravitational collapse could dominate on the larger scales. The universe would no longer approach the quiet horizon-bounded equilibrium we have been describing. The first uncertainty therefore sits beneath almost everything else. What does dark energy become? The Google year answer assumes that it remains close enough to a permanent positive cosmological constant for the standard causal patch future to survive. The second challenge is more abrupt. The vacuum itself may not be absolutely stable. In quantum field theory, what we call empty space is not simply nothing. It is a physical state associated with fields and their lowest available energy configuration. The vacuum we inhabit may be the true lowest energy state, or it may be metastable. A metastable vacuum can survive for an extraordinarily long time while still possessing a possible transition to a lower energy state. If such a transition occurred, a bubble of the new vacuum could form through quantum tunneling. The bubble would expand outward at nearly the speed of light. The laws and constants governing particles inside it could differ from those outside. Atomic structures might no longer be possible. Protons, electrons, and the interactions holding matter together could behave differently or cease to support anything resembling the universe we know. No warning signal could arrive ahead of the boundary. The change itself would travel almost as quickly as any warning could move. For the far future timeline, the important point is simple. Vacuum decay would not adjust the black hole clock. It could end the scenario before the clock finishes. A transition might occur tomorrow. It might occur after 10 to the power of 50 years. It might never occur. Current physics does not provide a confirmed scheduled lifetime for our vacuum. So vacuum decay cannot replace the standard forecast with a better date. It remains a conditional interruption, a process that could prevent the universe from ever reaching the particular heat-death route we have mapped. The third challenge appears at the end of black hole evaporation. Our calculation assumes that Hawking radiation continues until the black hole loses all its mass. Semi-classical physics describes the long evaporation process extremely well in regimes where the black hole remains much larger than the scale at which quantum gravity becomes dominant. But near the final stage, the approximation fails. The black hole becomes extremely small. Its temperature rises. Space-time curvature near the object reaches regimes where a complete quantum theory of gravity is required. We do not yet possess an experimentally confirmed theory that describes that final moment. The black hole may disappear completely. That is the usual assumption. But some proposals allow a stable remnant to remain. Such a remnant might contain roughly the Planck mass or another tiny amount of residual mass. It could potentially preserve information or represent a final quantum gravitational state. If stable remnants exist, the last black hole does not end in perfect absence. It leaves something behind. Would that prevent heat death? Not necessarily. A population of tiny stable remnants could survive while remaining cold, isolated, and unable to support significant organized activity. Their existence would change the inventory of the final universe more than its practical usability. But they could alter the strict entropy accounting. If remnants retain large numbers of hidden internal states, theorists must explain how they avoid producing other physical problems. If they retain only limited information, they may not resolve the deeper questions that motivated them. The possibility is real enough to preserve as an uncertainty. It is not established enough to replace complete evaporation as the main path. The fourth uncertainty returns us to ordinary matter. Protons may be stable. If they are, cold baryonic objects can persist much longer than they would in proton decay models. Black dwarfs, planets, fragments of matter, and isolated particles could remain after the stellar era without gradually dissolving through baryon number-violating decay. This changes the late universe's contents. It can also create extremely rare future events. Stable remnants may collide, tunnel into new configurations, or be captured by black holes across staggering timescales. But stable matter does not automatically defeat heat death. A perfectly durable object can become thermodynamically useless. It can cool until it nearly matches its environment. It can drift beyond contact. It can remain separated from every available energy reservoir. The difference between survival and usefulness remains decisive. Proton stability changes how much structure remains. It does not guarantee that the remaining structure can continue performing work. The fifth challenge comes from extremely rare fluctuations. A system near thermal equilibrium does not become absolutely motionless. Quantum and thermal fluctuations may still occur. Given enough time, a rare fluctuation could temporarily produce a lower entropy arrangement inside a small region. Particles might gather. A complex pattern might appear. Under some speculative discussions, even an observer-like configuration could emerge briefly from equilibrium fluctuations. These possibilities are famous because the available future may be enormously long, but they do not restore the universe as a sustained engine. A fluctuation borrows no exception from the second law. A local entropy decrease can occur as part of a larger statistical system, but the overwhelmingly probable direction remains toward equilibrium. A rare pocket of structure appears. It dissolves. The larger state persists. Fluctuations complicate the meaning of nothing ever happens again. They do not provide a durable escape from heat death. So the alternatives can now be ranked. A changing dark energy state could rewrite the entire cosmological boundary and final equilibrium. Vacuum decay could terminate the standard future before its longest stages. Unknown quantum gravity could leave a stable black hole remnant. Stable protons could preserve cold ordinary matter. Rare fluctuations could generate isolated temporary departures from equilibrium. Only the first two can clearly destroy the entire standard timeline at a foundational level. The others modify what remains after useful gradients have largely disappeared. This is why the practical answer must carry conditions. Roughly 10 to the power of 100 years, if cosmic acceleration continues in a de Sitter-like form, if the vacuum remains stable, if Hawking evaporation proceeds without a permanent massive remnant, and if no unknown process intervenes first. The number is not a prophecy. It is the endpoint of a model. And after testing the strongest ways that model could fail, we can now return to the path it predicts. One causal patch, one final major black hole, a shrinking horizon inside a larger cosmological horizon, radiation spreading outward, localized entropy falling while generalized entropy continues to rise. The final object does not disappear from an empty background. It disappears into a thermodynamic system whose largest component is the boundary of accessible space itself. One quantum leaves the black hole. It carries almost no energy by any familiar standard. The hole is still enormous. Its temperature is extraordinarily low. The interval before the next emission may exceed ages that once contained stars, planets, and entire galactic histories. The quantum moves outward. Behind it lies the black hole horizon. Ahead lies the cosmological horizon of the causal patch. Almost nothing else remains between them. This is the final physical system. The black hole is the last major localized concentration of mass. The cosmological horizon defines the outer limit of accessible events. The space between them continues expanding. The emitted quantum travels locally at the speed of light, but its wavelength stretches with the geometry through which it moves. Its energy becomes increasingly dilute. The black hole has lost a minute amount of mass. Its horizon area has fallen. Its own entropy has decreased. The radiation outside now carries additional entropy. The geometry of the causal patch has changed by an almost immeasurable amount. The generalized entropy of the full system continues moving upward. For most of the black hole's lifetime, this sequence repeats without visible drama. A quantum leaves. The horizon contracts. The surrounding radiation disperses. An immense interval passes. Another quantum leaves. There is no planet nearby to absorb the energy. No machine converts it into work. No colder reservoir is arranged beside a warmer one in a way that could sustain an engine. The radiation contributes to dispersion, not renewed structure. The black hole still preserves a difference. Near it, space-time is strongly curved. Its horizon has a temperature distinct from the larger cosmological environment. Its mass creates a localized feature inside the patch. As long as that feature remains, the system has not reached its highest available generalized entropy. The black hole keeps part of the patch's energy concentrated. Its evaporation dismantles that concentration. As the mass decreases, the hole grows warmer. The emissions become more frequent. The long intervals begin to shorten. For almost the entire lifetime, the change was too slow to imagine as motion. Near the end, the same physical relationship creates acceleration. Less mass, higher temperature, greater radiated power, faster loss. The horizon that once survived beyond every star begins collapsing through its remaining scales. The final stage approaches the regime where semi-classical physics can no longer describe every detail confidently. Quantum gravity becomes unavoidable. The standard scenario allows the black hole to disappear completely. Other proposals leave a tiny remnant. That unresolved instant matters to a complete theory of nature. It matters less to the practical thermodynamic verdict. Long before the final Planck scale question is settled, the major localized reservoir has been lost. The hole no longer contains a galactic mass. It no longer stores the enormous horizon entropy that defined the black hole era. Its capacity to power any significant future process has vanished. The released energy is spread through the patch. The black hole horizon shrinks out of the macroscopic world. The cosmological horizon remains. Under a permanent positive cosmological constant, the patch approaches the empty de Sitter-like geometry associated with that horizon. Empty does not mean that physics stops. Quantum fields remain. The horizon has a tiny temperature. Fluctuations can occur. Radiation may persist in forms stretched beyond any practical concentration. But the patch no longer contains a comparable localized system capable of sustaining organized work. The outer horizon now dominates the entropy accounting. This is why the final state can look almost featureless while possessing an immense entropy. Visible complexity has disappeared. The number of inaccessible microscopic configurations associated with the horizon has not. The late smoothness is not the same as the early smoothness. The early universe was nearly uniform, but small density differences could grow. Gravity could amplify them. Gas could collapse. Stars and galaxies could form. That smooth state contained unrealized structure. The final smooth state has spent the available structure. The major gradients have already driven their processes. There is no dense cloud waiting to collapse. No fuel reserve waiting for ignition. No second black hole approaching from beyond the horizon. No external galaxy capable of entering the causal patch and rebuilding the lost concentration. The patch has not merely become dark. It has become thermodynamically closed against the large-scale histories that once renewed it. The last quantum continues outward. Its wavelength stretches. The black hole behind it becomes smaller. When the horizon finally disappears, or becomes only a microscopic remnant, the outgoing radiation has no large localized source left to replace it. The practical countdown is complete. The system may still require an unlimited mathematical future to approach perfect equilibrium exactly. Tiny deviations may remain. Fluctuations may disturb the background. The strict maximum may be a limiting state rather than an event reached at one finite time. But the distinction between active cosmic history and passive approach has already become clear. Before the final evaporation, a macroscopic black hole remains. After it, no major localized free energy reservoir survives inside the patch. That is what the googol timescale measures. It does not measure the destruction of existence. It measures the disappearance of the final large object capable of keeping the accessible region meaningfully away from equilibrium. One quantum travels toward the outer horizon. Behind it, the last great concentration is ending. Ahead of it, the entropy of the boundary dominates the future. So how long until the universe reaches maximum entropy? The practical answer is approximately 10 to the power of 100 years. A googol years. That is the broad time scale on which the largest black holes expected inside a future causal patch may finish evaporating under the standard scenario. The number is not the lifetime of the last star. Ordinary stellar activity ends far earlier, broadly near the 10 to the power of 14-year scale. It is not a predicted date for proton decay. Proton decay has never been observed. It is not a universal alarm that rings everywhere in the cosmos at the same moment. The number comes from black hole thermodynamics. Black holes emit Hawking radiation. Larger black holes have lower temperatures. Their evaporation lifetimes rise approximately with the cube of their mass. A stellar mass black hole may survive around 10 to the power of 67 years. A million solar mass hole moves toward 10 to the power of 85 years. A billion solar mass hole moves toward 10 to the power of 94 years. Future mergers and captures can assemble larger holes inside gravitationally bound regions, pushing the longest plausible local lifetimes toward the googol year range. That is the mechanism. The measurement itself requires a clear reference frame. We are not assigning one finite entropy clock to an entire, possibly infinite universe. Under continued accelerated expansion, unbound regions become causally disconnected. Their future signals can no longer reach one another. Each accessible region develops its own thermodynamic history. The practical question is therefore, how long until one causal patch loses its final major localized reservoir of usable free energy? The largest surviving black hole supplies the clock. While it remains, the patch contains a macroscopic concentration of mass with its own horizon, temperature, and entropy. The hole is colder than almost everything that existed during the stellar era, but it is still different from its environment. That difference allows continued evolution. The black hole emits. Its mass changes. Its horizon shrinks. The surrounding system has not yet reached equilibrium. When the hole finally evaporates, its concentrated energy becomes diffuse radiation. The radiation spreads across the expanding patch. Its wavelengths stretch. The cosmological horizon dominates the remaining entropy budget. No comparable localized engine remains to replace the black hole. This is the practical heat-death threshold. It does not mean every particle vanishes. It does not mean all energy is destroyed. It does not require absolute zero. Energy can remain in radiation, quantum fields, microscopic remnants, or horizon-scale thermal behavior. What disappears is access to a useful gradient large enough to support sustained organized work. The system still exists. It has almost nothing left to spend. That verdict depends on assumptions. First, dark energy must continue producing a future sufficiently close to the permanent positive cosmological constant model. If dark energy evolves radically, the cosmological horizon and final equilibrium can change. Second, the vacuum must remain stable. A vacuum transition could interrupt the black hole timeline before the longest lifetimes are completed. Third, Hawking evaporation must continue through the macroscopic lifetime of the hole. The final microscopic stage requires quantum gravity, and present theory does not determine with certainty whether complete disappearance or a tiny remnant occurs. Fourth, no unknown process can generate a new large reservoir after the ordinary cosmic inventory has been exhausted or isolated. These assumptions do not reduce the answer to speculation. They define the model to which the answer belongs. The known laws of thermodynamics, general relativity, and quantum field theory in curved spacetime create a consistent causal chain. Stars spend nuclear and gravitational gradients. Remnants retain weaker thermal, orbital, and rotational gradients. Gravitational encounters merge, capture, or eject the surviving objects. Black holes become the longest-lived localized reservoirs. The largest black holes evaporate last. Their disappearance leaves the causal patch near its highest available generalized entropy state. The exact exponent is less secure than the chain. A different final black hole mass changes the lifetime. A different dark energy future changes the horizon. Unknown quantum gravity changes the final instant. But within the standard scenario, the order of magnitude remains the honest answer. Approximately 10 to the power of 100 years. One final distinction prevents that answer from becoming misleading. The universe may reach a practical maximum before it reaches an exact mathematical maximum. After the last major black hole disappears, dilute radiation and horizon-scale thermal behavior can remain. Tiny fluctuations may occur. Small deviations from equilibrium may continue fading. The system can move closer to its maximum generalized entropy without becoming exactly identical to that limit at a finite ordinary time. In that strict sense, the universe may never arrive. It may approach forever. This is not a contradiction. A physical system can lose every usable macroscopic gradient while microscopic fluctuations continue. For any engine, organism, star, or civilization, the process is over. For an exact mathematical description, the limiting state may remain infinitely far ahead. The title therefore has two correct answers. For practical heat death, approximately a googol years, under the standard cosmological and black hole assumptions. For perfect exact maximum entropy, possibly no finite time at all. The first answer tells us when the final major engine disappears. The second tells us that equilibrium can be a destination approached without a final footstep. The number has now done its work. What remains is not another calculation. It is the physical meaning of a universe that still contains energy after it has lost every important difference. Return to the warm object beside the cold one. At first, the difference can be felt. Heat flows from one side to the other, a machine placed between them could move, a current could be generated, something organized could use the imbalance before it faded. Later, the temperatures approach each other. The energy remains. The opportunity weakens. The universe has followed the same movement across its entire history. Its first great differences did not look like finished stars or planets. They were small variations in density, temperature, and motion. Gravity deepened them. Matter fell inward. Gas heated. The first stars ignited. Each star held open a temporary path between a hot interior and colder space. Light moved through that path. Around some stars, planets intercepted part of the flow. Weather turned. Oceans circulated. Chemistry became active. For a time, a small world could remain far from equilibrium because a star was spending fuel nearby. The star did not preserve the difference forever. It used it. Every photon carried part of the concentrated energy outward. Every second of light moved the larger system toward a state in which less of that energy could be gathered back into useful form. The beauty and the loss were the same process. The final stars continued much longer than the bright stars of the present sky. Small red dwarfs released their energy with extraordinary patience. But even patience consumes fuel. The last stellar surface eventually cooled. The final ordinary light travelled outward and was not replaced. Darkness followed. Gravity continued. Cold remnants moved through old galactic structures. Some escaped, some collided, some fell inward. Over immense time, the remaining matter was separated or gathered behind horizons. One black hole survived longer than every familiar object around it. It contained the final great concentration. Its horizon was dark, but the darkness was not in activity. Quantum fields continued their work. The hole possessed a temperature. It emitted radiation so weakly that almost all of its lifetime passed in silence. One quantum left. Then another. The black hole became lighter. Its horizon became smaller. The intervals shortened only near the end. There was no galaxy left to feed it. No neighboring star warmed the patch. No distant region could send a new reservoir across the cosmological horizon. The black hole was the last large difference between one place and another. Near it, space-time still curved around concentrated mass. Farther away, the causal patch approached its empty horizon-dominated state. As long as the hole remained, the system could still change in a major localized way. Then the final macroscopic horizon disappeared. The energy entered radiation. The radiation spread. Space stretched its wavelength toward the outer boundary of accessible events. Nothing had been erased from the physical accounting. The concentrated form had been lost. This is the part human intuition resists. We are accustomed to endings that destroy something. A flame goes out. A structure collapses. A body stops moving. Heat death is quieter. The universe does not need to lose all its contents. It needs only to lose the differences that allow those contents to participate in sustained, organized change. A photon can remain. A field can fluctuate. A tiny remnant may survive. The cosmological horizon can possess a temperature. None of these facts guarantees a new star, a new world, or a new engine. Energy without an accessible gradient is not a reserve waiting to be used. It is an inheritance that has already been dispersed. The final state may never become perfectly exact. A fluctuation can briefly disturb the background. A quantum can appear. A microscopic arrangement can depart from the most probable one. But no large causal ladder remains to carry that disturbance into a new era of structure. There is no dense cloud waiting nearby. No cold external universe remains available as a sink. No reservoir stands ready to feed a cycle. A ripple appears. It fades. The larger equilibrium survives. The warm object and the cold surroundings have become one condition for every practical purpose. No machine can be placed between them because there is no longer a meaningful between. The cosmic story began with differences capable of growing. It ends with differences too small, too dilute, or too inaccessible to matter. A final quantum continues through the patch. Behind it there is no black hole now, only the fading consequence of the horizon that once emitted it. The quantum passes through a region without planets, instruments, or eyes. Nothing intercepts it. Nothing converts its energy into motion, memory, or warmth. Its wavelength stretches. Its energy thins. Ahead lies the cosmological horizon, the boundary beyond which no future message can return. The quantum approaches that boundary without spectacle. There is no final audience. No clock displays the googol thier. No voice announces that the last major engine has stopped. The practical ending has already occurred in the absence of anything capable of naming it. The remaining patch continues approaching its equilibrium. Closer, then closer again. Not because every microscopic event has ended, but because no event can rebuild the differences that once made cosmic history active. The stars spent one kind of difference. Gravity spent another. Black holes held the final concentrations for almost all the remaining time. Their radiation released those concentrations into the horizon-bound dark. What remains is energy without leverage, motion without a useful direction, existence without a significant gradient from which a new organized future can be drawn. The last quantum stretches toward the horizon. The universe has not run out of energy, it has run out of differences.